Okay, before we get rock and roll, I'm still doing some stuff in the background, but do you guys have any questions from the advising video after watching it? If you had a chance to watch it, I don't mind answering any questions. Okay, good to go for the lecture. Let me bring this up just a little bit. Hold on. Eyeball it a little. There we go. That's good. I don't understand why it's not in focus, because it could clearly be better in focus. But anyway, okay, whatever. Let's get started. So today we're going to talk about the logarithm. And if you've never heard this word before, that's fine. I go over it like you have not heard of it. But before we get there, let's talk about really where it came from. It came from the exponential function. So if we look back, and I'm going to write this exponential function as just an equation, y equals, let's say y equals 2 to the x power, doesn't matter. At some point, some mathematician said, what if I wanted to take the inverse of this? And if you take the inverse, remember you switch the x and the y values. So you wind up with x equals 2 to the y. And there was an issue there because the y value is in the exponent. And we can take the inverse. If you want to graph the exponential, let me turn that off. It looks something like this, which it passes the vertical and horizontal line test. So we can take its inverse, but to do so, mathematicians had to create a new notation. I have lost my cell phone. Hold on. Let me put this on silent real fast. So they had to create a new notation, and this is where it comes from. So I'm going to kind of show you right here is the exponential form. And then to put this into logarithm form, the exponent is by itself. So it's y equals, and then it would be log base 2, because that's the base over here. Now, we're going to write that as a subscript. So log base 2, and then whatever's by itself, x. So it turns out these two equations are the exact same. It's just two different ways to write the same exact thing, okay? Two different ways to write the same exact thing. Now, so let's look at this for now. We're going to come back and just go back and forth between the exponential and the logarithm here in a minute. But let's define a few things. So this is considered our base. Now, there's only a one rule about it. It's that the base has to be greater than 0 and it can't be 1. It should sound familiar. It's the same with the exponent, right? Remember, the exponent had to be greater than 0. It just can't be 1. Not a big deal. And it turns out whatever is inside this logarithm also has to be greater than 0. So this has to be, I'm just going to put greater than 0 for now. I'm going to come back to that when we talk about the domain of the function, the logarithmic function. We'll get there. But for now, we're going to focus on just going back and forth between exponential term and a logarithm, I should say exponential equation and a logarithmic equation, okay? So all I'm going to do now is just write these back and forth. So we're going to start with an exponential equation, and we're going to turn it into a logarithmic equation. So the most basic example is x equals b to the y, okay? X equals b to the y, where b is some base. If I wanted to write that as a logarithm, now the exponent goes by itself, log base, whatever the base is over here, of whatever's by itself over there. So x equals b to the y is y equals log base b of x. Let's do one that is in our calculator. The log button in your calculator down here, that log button by number 7, it's log base 10. So let's write something that we know. We know 10 squared equals 100, right? I'm going to write it like this just to keep it in the same kind of form we have going on. So 10 squared equals 100. Well, what that means, if we wrote that as a logarithm, is that 2 equals log base 10 of 100. Now, log base 10 is a special log. I forgot what, I think your book calls them common logarithms. So if it's a log base 10, you don't have to write the base here. So this would be log of 100. It's an assumed 10 if nothing is written. So I'm going to check this on the calculator just to kind of show you how to pop it in the calculator. It's really easy. All you got to do is press the log button right there. And so it says log. Mine says log parentheses. Some of you guys, it does give you the log with a base. Mine says log parentheses, and I'm going to put in 100. I'm going to hit enter, and you'll see it pops back 2. Kind of cool. Okay. So that works for log base 10. If I don't have log base 10, I have to use something different. We'll get to that later. Okay. Let's do, well, we could probably fit one more in here. Let's say I'm going to write it how we typically write it. Like, let's say 5 to the negative 1 equals 1/5, right? If you raise something to a negative power, it just equals 1/5. I'm going to write this as a logarithm. Now, remember, guys, whatever's the exponent is first. So that the negative 1 is the exponent. Negative 1 equals log base. Now our base is 5 of, and then whatever's by itself is in here. So negative 1 equals log base 5 of 1/5. Okay. Any questions about this? I'm going to do a few more. Actually, I'm going to give you a few, and I want you to try them just to make sure that we understand what we have going on here. Okay. But any questions about this other than, okay, I need to see a few more examples. Okay. I'm going to give you the log. We're going to go vice versa here in a second. We're going to go the other way here in a minute. And I want you to give me, oh, shoot, I wrote it backwards. I'm going to give you the exponent, and I want you to give me the logarithm. Okay? Let's do another. Let's do like, I know that 2 cubed equals 8. Try that one. 2 cubed equals 8. Let's do one where we don't necessarily know what it is, and it brings up a new example for us. Let's say e to the z power equals 3. So just write that. That's a z right there. E to the z power equals 3. And then, let's do a square root. Let's say 25 to the 1/2. We know that means the square root of 25 equals 5. So I'm going to give you just a minute or two to write these as logarithms. So I'll give you 1 minute just to write these 3 as a logarithmic equation. Let's try it. So 2 to the third equals 8. That's going to be 3 equals, can you see that? I think this marker is just too faint. 3 equals log base 2 of 8. Now, E, let's talk about this one for a minute. So this is a Z up here. So it'd be Z equals log base E of 3. Now, log base E is another common logarithm. So just like 10, it actually has a button in the calculator, but you have to know what it means. So log base E is called the natural log, and it's written kind of backwards, log natural. So it's ln of 3. These mean the same thing. Okay, let me get rid of this marker. It's just like that. Those mean the same exact thing. And you'll see in your calculator, you've got that button. It's right underneath the logarithm. So the ln, so if I put in like ln3, I can get the actual number for that, 1.0986, whatever. Okay, so it's kind of nice. So ln or log base E and log base 10 are both automatically in your calculator. So let's look at this one. This would be 1/2 equals log base 25 of 5, right? So log base 25 of 5 would be 1/2. Kind of cool. I know. You don't have to tell me. I get it. Okay, so now I want you to go the other way. I'm going to give you a few more examples, but I want you to go from logarithm now to exponential. So let's say I gave you a equals log base b of 6. 2 equals log of y. Let's do an ln in here one. Yeah, let's say q equals ln of 4. And let's do one that works here. Let's do 1/3 equals log base 8 of 2. So try those now. So I'm giving you the logarithm, and I want you to put this into exponential. Okay, I'm giving you the logarithm, and I want you to put those in exponential. I'm going to give you just a few minutes. Okay, let's check to see if we get this. Let's see if this orange shows up. A equals log base b of 6. So now the b is the base. Oh yeah, it shows up for you. B, now we're going to raise it to the a power equals 6. So b to the a equals 6. So now the log, remember if there's nothing there, it's a 10. So this means 10 squared equals y. Now we know that's 100, but that's kind of neat. Okay, so 10 squared equals 100. I'll get to that. Hold on one second, Sherry. And then the ln, remember this is ln base e. So it's e to the q equals 4, okay? And then lastly, 8 to the 1/3 equals 2. Now, sure, yeah. Why are you using parentheses on some and not others? It doesn't matter. Yeah, and I'll tell you, sometimes we're going to get to some. Here, I'm going to turn this sideways to have a little more room here. We're going to get to some that you need it whenever you have more than one term. So if I had like a log base 3 of x plus 1 equals 2, and I wanted to put this into exponential form, I need that because if I didn't write the parenthesis, it would look just like x, only x was inside the logarithm, right? So if you have more than one term, you will need parentheses. Now, notice all the ones we've done so far, there's only been one term because we're kind of at the basic. We're at the baby step level, right? This is more in a few days. Actually, I think in the next lecture, we'll be talking about this. Maybe at the end. I mean, think if I wanted to put this into exponential, the base is 3. I'd raise it to the second power, and it would equal x plus 1. It turns into something we can easily solve, right? 9, subtract the 1, you wind up with 8. So, but yeah, that's why. I know that's kind of a long answer to that question, Sherry, but it doesn't matter. But if you have more than one term, you do have to use parentheses. Good question. Yeah. So let's make sure I'm not forgetting anything early on. I don't think I am. Yeah. I'm gonna So I'm gonna do something a little backwards than the order of your book because I think that your book kind of goes in it too quickly. Your book goes over 4 basic properties of logarithms, and we're going to use these properties to simplify. Okay, not to solve. This is simplification, but basic properties of, we'll say, logs. Okay, and they're kind of neat, and we can show why they're true here in a second, though. The first rule says, look, if you have any logarithm with base b, b can be whatever it wants to be. But if you've got a log base b of that exact same thing, so these two match, this winds up equaling 1, okay? This winds up equaling 1, which is kind of nice when you're simplifying. So it can get rid of a logarithm if we're simplifying everything going on. So let's look at why this happens. Let's say I started with log base, 4 of 4, and it equaled y. I want to show why that's 1. Well, I'm going to write this as an exponent. Okay, I'm going to write as an exponent over here. So as an exponent, this would be 4 raised to the y power equals 4, right? Well, the only thing you can raise to a power, the only thing an exponent can be when you raise it to a power and it stays the same is 1. Okay, so that's where it comes from. It actually comes from putting this into exponential form and realizing, hey, these have to be just 1. The exponent has to be 1. But that is the rule. We don't have to do this every time. We can just say, hey, you know what? If we take the log of the same base, just equals 1. The second one that your book goes over says, well, what if we take the log of some base of 1? Well, it turns out it doesn't matter what the base is. If you're taking the log of 1, it always equals 0. Okay, and we'll kind of show this again with, I'll use that 4 example. So if I had like log base 4 of 1, and I want to know what does it equal? Why is it 0? Well, if I wrote it as an exponent, it would be 4 to the y power equals 0. Nope, I lied, didn't I? Wait. I wrote this wrong, didn't I? Why did I get a 0 here? Hold on, guys. It would be 4. I said 4 and wrote y. Whew, man, it feels like a Monday. 4 to the y power. There it is. 4 to the y power equals 1, right? That's, if I wanted to write this as an exponential equation, it would be base 4 raised to the y power equals 1. Well, if you want to raise anything to a power and it equal 1, it has to be 0. Anything raised to the 0 power is 1. So therefore, y equals 0. Anything raised, it doesn't matter what this base is. If you raise it to 0, it's always going to equal 1. So that's why we have that second rule. Okay, I'm going to combine these here in a minute, and we'll use them as we go. The third rule, which is probably used the most often for simplifying, says if we have log base b of b to the x power. Okay, so if you've got it kind of like number 1, where you've got the same base inside the logarithm as the base, then it turns out all this simplifies. It goes away, and it leaves you with x. I'm not going to show you why. Take my word for it. You can do that. If you want to know why I'm making an exponential equation, you'll see it. B to the x just equals b to the x, right? If I wanted to make this as an exponent, b to the x equals b to the x. So it has to be, okay? So let's use these with simplifying. So I'll try to sneak in an example here at the bottom of this one. If I had, let's say, and it'll say simplify completely. Use basic properties of logarithms to simplify completely. We'll call it A. If I've got log base 9 of 9 plus, I don't know, I want to put A there, log base, let's say 2 of 16. Log base 9 of 9 plus log base 2 of 16. Well, log base 9 of 9 lines up with this first property, right? It says if I've got the same thing, it just equals 1. So this is just going to turn into 1. Now, this property does, or this logarithm doesn't line up to the first or second. It's not that they're the same. It's definitely not that the 16 is a 1. So I'm going to see if I can get this number into a base 2. And I can, right? 2 times 2 is 4, times 2 is 8, times 2 is 16. So log base 2 of 2 to the 4th. So 2 to the 4th is 16. Okay? So 2 to the 4th, those are the same number. And then I can use this third property. It says, now don't forget the 1 plus log base 2 of 2 to the 4th. Well, that's just 4, because that's what the third property says. 1 plus 4 is 5. Okay? Question about that, other than, I need to see a few examples of that. This is kind of goofy because it's brand new. I don't know what you're talking about, Mr. Shirley. And I understand. This is new. It's a new language in a way, or a new notation in a language that we might not be comfortable with. Okay? So we're going to go over a lot of examples. Today's going to be very example driven. Okay? Okay, so let's look at another one, and I don't know if I could just do this. Actually, I have a clean piece of paper. Got a lot of marks on just so I can have the rules on the page here and I can refer to them, I'm going to do this. So we did A down here, let's do B. Let's say I've got log base 4 of 16 plus ln of 1. So I want you to try, well, actually, let's talk about this one. Log base 4 of 16. Now, it's not going to be one of the basic examples because the base isn't 1 and it's definitely not the same. But the idea is to think, hey, yeah, that's a great question. We're trying to simplify both of these using these properties. We're simplifying these logarithms using these properties. So let's go back to this log base 4 of 16. So log base 4 of 16, the goal is to think, can I get what's inside the logarithm into the same base that's written? Hold on. Yeah, and I can, right? 16 is 4 squared. And now plus, I'm going to come back to that ln1 here in a minute. And log base 4 of 4 squared, well, that's going to leave me with just 2 because this property says if I've got the same base inside of a base, it leaves me with whatever the exponent is. So this would be 2 plus ln of 1. Okay, so I've got the first one simplified. Now let's turn our attention to the second one, this ln of 1. Now, ln of 1, notice the 1 is inside the logarithm. Now remember, this logarithm is log base e, but it doesn't matter what the base is because the second property says, look, if you take the log of any base of 1, it just equals 0. So ln of 1, because it lines up with this property, is going to be 0. So it's 2 plus 0. You wind up with just 2. Okay? You wind up with just 2. Okay. Let me find another example here. Let me think of one. Let me think of this one. This one, I'm going to throw a few curveballs at you, but they're not too bad. You just have to remember some notation things. Let's say I had log base 2 of the square root of 2 minus, let's say, log of 10. Okay, log base 2, the square root of 2 minus log of 10. So the goal again is to simplify completely. We're going to simplify these where really we simplify out the logarithmic equation. Okay, we're going to simplify out the logarithmic equation. Okay, so let's look at this first one. The first one, you've got log base 2 of the square root of 2. It's not the same. I mean, there is a 2 and 2 there, but you got the square root going on. So it's not going to be 1. It's not 1 already. So we have to remember that if you've got a square root, it's the same as writing it as 2 to the 1/2. So I can rewrite this as log base 2 of 2 to the 1/2 power. It's the same exact thing. So we know from that third property that this is going to leave us with 1/2. Okay, that's going to leave us with 1/2. But over here, I've got log of 10. Oh, now remember, if you got log of 10, the base here is actually 10. We don't write it because it's 10 and it's assumed, but we've got the same thing going on. So the same thing means it leaves us with just 1. Okay, log base 10 of 10 is 1. Or you could say just log 10 because we know that it's base 10. Now this first term, log base 2 of 2 to the 1/2, that winds up being 1/2. Minus 1, that's going to be negative 1/2. Negative 1/2. All right, these aren't, I'm not trying to tell you these are easy. This is not, and this is brand new. Once you go through the homework, it gets easier. This is definitely one of those you have to, you can't just watch a lot of these and just kind of get it. You gotta get into the arena. Okay, get a little dirty. Okay. Oh, there is one more rule, and it's not used that often, so that's why I kind of waited to go over it. It's the fourth rule, and it says if we have a base raised to the log base b of x, so these match. A base raised to the log base b of x, that just equals x. And now you'll see these on page 462 at the very bottom. It puts them together with the log base 10 for some reason. But if you look at page 462, at the bottom, it puts these all together. Okay? It puts these all together. I'm going to steal some now from the homework. I thought they did addition and subtraction. They just give you one at a time, which is a lot easier. Okay? So I'm going to steal some of these, and I want you to try them, and you've really got to use your thinking brain. Okay? You've really got to think kind of a little bit outside the box on some of these. But if you don't get them, don't get too disheartened because we'll go over them. So I'm looking at your homework. This is on page 466. Let's do number, I'll do the even ones. Let's do 24. Log base 3 of 27. Then let's do 28. Log base 3 of 1/9. And then let's do 34. I'll write that one over here. 34, which is log base 81 of 9. And I'm telling you, these are not easy. I'll give you a few minutes. It's okay to just be upset that you don't get them. Okay, but just try as hard as you can and just attempt it. Okay. Let's see if I can attempt these. Log base 3 to 27. That's not bad. I got to think, can I get 27 in base 3? Yeah, that's just 3 to the third, right? 3 times 3 times 3 is 27. So look, these cancel. The log base 3 of 3 cancels. It leaves us with the exponent. So we wind up with just 3. Now, man, I'm telling you, 28's not as easy. And I'm going to show you where my brain goes with this one and how I get there. Okay, so I'm going to show you every little step along the way. First off, I can get 9 into base 3. I'm going to do that first. It doesn't solve our answer, though. It doesn't simplify this function yet. 9 is 3 squared, right? So at least we have the same bases. The issue, though, is that this is in the denominator, right? And we learned, if you've taken a prior algebra class, you've learned how to move exponents from denominators to numerators and vice versa. And the way to do that was actually negating the exponent. So log base 3 of 3 to the negative 2. 3 to the negative 2 is 1 over 3 squared, which winds up simplifying into 1 over 9. It's not the easiest question. That's what I'm going over. Okay. The last part's the easy part, the actual new rule we learned, which is says, hey, if you've got log base 3 of 3, that cancels and it leaves me with negative 2. Okay. So they're throwing some tougher examples at you. Not too bad. Okay. I think 34 is probably the hardest one that they can kind of throw your direction. We've got log base 81 of 9. Remember, the goal is to think, what can we raise 9 to get an 81? Well, that doesn't make sense. Wait, no. Our goal is to get 9 into a base 81, right? Like we got 27 into a base 3. We got this really 1/9 into a base 3. So the goal is to get this 9 into an 81. So we need to think, what do we do to 81 to get 9? Well, you can divide it by 9, right? 81 divided by 9 is 9. But we need to think of it in terms of exponents. What's the square root? Right? The square root of 81 is 9. And this gets us into the same base. Okay? Now we know that the square root doesn't do anything. We have to write it as an exponent, like that previous example. And then it leaves us with the 1/2. Okay, I think this is the hardest one because it's hard. You really kind of have to think outside of the box a little bit. And it's just, if you've never seen logarithms before, this is the tough question. Okay, it's a pretty tough question. I want you to know that now. It's okay if you're frustrated and throwing your hands up in the air saying you don't understand that. I get that. This takes a little bit of time to understand. Doing the homework, getting upset at the homework, and then trying it again, and then getting upset again. And then eventually it'll click. Okay, so let's go on to the next topic, which is the domain. Domain of logarithmic functions. I said I would talk about this earlier when we were kind of going over a function. Let's look at one of these that's written as a function. So it'd be like log base, or f of x equals log base 2 of x plus 4, something like that. Okay, this would be a good example of a logarithmic function. Now remember, the base here, all the rules apply. That 2, whatever's written there, has to be greater than 0, and it can't be 1. So 2 is fine. It's greater than 0. It's not 1. But there's a rule that goes with the domain of these, and it's what's inside this logarithm, right? Remember, your x value is going to be inside the logarithm because that was the whole point of taking the inverse, that very first thing we talked about. It puts the x value inside the logarithm. So we got to talk about the domain. It turns out whatever's inside this logarithm has to be greater than 0. So the easiest way to explain this is by this example. So I'm going to take whatever's inside here. So if I ask you for the domain, I'm going to take whatever's inside and make it greater than 0. Not greater than or equal to. You can't take a logarithm of 0. You can try it on your calculator. If you put in like ln of 0, you should get back an error. But you get x plus 4 is greater than 0, subtract the 4. Turns out x has to be greater than negative 4. Now, written as an interval, remember we're going to use parentheses because we can't equal it. So negative 4 to infinity. Okay? So if we look at another one, and all I'm going to do is ask you for the domain. Should I kind of split this up? Let's say we got f of x equals log of 3 minus x. Log of 3 minus x. Now, remember, the log just means it's base 10, no big deal. And I'm going to ask you for the domain. And the domain says, oh, whatever's inside here, we have to put greater than 0, right? That's greater than 0. So if we want to solve this one, we can move the x over. We get 3 is greater than x. Now, to really kind of make this one make sense, you got to put the x on the other side. So what you can do is you can flip these. As long as the open side stays to whatever the open side's on and the closed side's for the closed side. So this is the same as x is less than 3, right? X is less than 3. So if I'm going to write this one out, it would be negative infinity to 3. So that would be my domain. So whatever's inside the logarithm has to be greater than 0. Now, it pops up maybe in like 3 or maybe 2 homework questions today. But when we get to 4.4, when we get into solving these logarithms, you'll see this again. So this is kind of just like a little introduction, and I'll bring it back up when we get to 4.4. But it is it's there, and I just needed to go over it. So it's not the first time that you see it when you get into section 4.4. Okay. Okay. Not a big deal. It's one of the easier things about the logarithm. Let's do an application question. These are always kind of fun, especially if you have a kiddo around this age, which is kind of neat. This is the application exercises on page 467. And it talks about the height of a girl who is X years old. So X equals years of age. This is number 113 and 114. Years of age. And we have this function that gives us the percent of adult height. Percent of adult height. Now, I think it pops it out in written as a percentage. We'll see. So let's say the function actually looks like this. F of x equals 62 plus 35 log of x minus 4. Okay, so now I think the girl has to be between 5 and 15. So x is years of age, and it only works from 5 to 15 because, before 5 you're growing exponentially. After 5 you kind of slow down. So does anyone in here have a daughter or a niece that's in between the ages of 5 and 15? And if you do, in the chat box right here, put in their age. And if you can get it to kind of like, if it was like 5.5 or 5, 6.5, it'll make it easier. So pop that in the chat box real fast, and we can use an example, a real life example. If you don't have one, I'll make somebody up. It's not a big deal. I'll give you a minute. If you got to think of how old your niece is, because you're going to talk to her in 4 years. Carry the one. Hey, Lauren's sister's 14. This is perfect. Now, Lauren, is she like close to 14? Or is she like 14 and a half? Like if you were like, how many months? 14 and how many months? She turned 14 in August. Okay, perfect. So she's only like 14. We'll say 14 and what? Is that August, September, October? Let's say 14 and 2 months. Now, 2 months is 2 out of 12, just to get a better approximation here. 0.1. Okay, we'll say that now, Lauren, if you don't mind me asking, what is her name? Lainey. Okay, Lainey is 14.2 years old. Okay, Lainey is 14.2 years old. And we want to know what percent of her adult height has she met so far. So all we have to do is plug it into this equation. So f of 14.2 equals 62 plus 35 log of 14.2 minus 4. It's a minus on a times. So I'm going to just kind of simplify this down. So 62 plus 35, that's 35 times if you want to write times, log of 10.2. Now, I've got to use my calculator for this, unless you know how to use a log ruler, whatever they used to be called, I'm not sure. But I'm going to pop this in the calculator. Notice this is log base 10, so it's in my calculator. So 62, I'm going to assume Lainey's close to her overall height, right? Because she's almost 15 and this works to 15, but let's see what it is. 62 plus 35 log of 10.2. 97.3. She's very close. So 97.3%. So Lainey, because she's so close to 15, and girls do, typically stop growing 15, 16, something in that range. Lainey has reached, on average, because this is just a model, it doesn't work for everybody, realize that. She's reached 97.3% of her height. Now, here's the real question, Lauren. Do you know exactly how tall Lainey is? If you don't, it's okay. This is for bonus points. Give you a minute to text her. She's at school, or she's at home now. I guess around 5. Let's say she's 5'6". Okay, we want to extend this concept out a little bit. So let's say she's 5.6. So or 5'6". Now I'm going to do this in inches because it makes more sense. So 5'6", 5'6" inches is 66 inches, right? We're going to keep it in just inches. It makes it a little easier. So here's what we're saying. If we want to know Lainey's overall height when she is an adult, we would take whatever her overall height is, we'll call it X, times, now 97.3, that's 0.973, and we'll get her current height, which is 66 inches. So her adult height is X. Now we're changing up the question. X is the adult height. Times, we know she's met 97.3% of it, and that's 66 inches. So I'm going to divide 0.973. I bet she's not going to get another inch here. Let's see. 66 divided, not 3, 66 divided by 0.973. 67 point, yeah, she's going to get, it's calling for her to be two more inches taller, right? So 66, that's right, 0.973, yeah. So 67.8. Now 0.8, now this isn't 8 inches, this is 8/10, right? So 0.8 would roughly be like 3/4 of an inch, right? Something more close to that. So it's calling for Lainey to be 6'7.75" inches. We'll do ish. Hey, so she might get another inch and a half still, because she's 14. Not that I don't know. That matters. Okay. Any question? This is just now. This last part was not in the homework. That was just me because I think it's an interesting example. I think it's the next section goes over male height for the height of boys. The same kind of question, but just the height of boys. We'll do that one too. I think what was it in this section? I know it's in here somewhere. And it's always an interesting one. It's modeled my son very, like I started doing this example back when he was like 7 or 8, and he's 15 now. And back when he was 7 or 8, it said he would be 6'3", and I laughed because no one in my family is 6'3", and right now he's like at 6'1", and he's 15. So it's pretty close, which is kind of crazy. Okay. Anyway, so let's get to homework. So in section 4.2, a lot of this homework is the stuff we talked about, kind of going back and forth between exponentials, understanding how to go back and forth, and then that common log base. So it's going to seem like I'm giving you a lot, but it's not, because it's a lot of it won't take long, but then there's a few questions that might take a while. 1 through 39 odd. Now all these are going to be odd. I'm not worried about graphing, just like I wasn't with the exponential. 75, 77. Going to be my 2 domain questions. And 81 through 103. And then 113 through 117. And all of these are odd. And I know you might be rolling your eyeballs right here, which is fine. I do have 2 meters. But these won't take as long as they look. And especially if you've never seen these before, it'll help you to hit this homework. It won't take long. It won't take long before you're like, oh, okay, I get it. This isn't as bad as I thought. Okay. Let me go back up here. Okay. You guys have any other questions? Any math questions, advising questions, anything? I'll stick around here for a minute. You guys are free to leave. I need to throw away my trash at Arby's for lunch. If you have any questions, let me know. I'll stick around. I'll be behind the scenes. I've got my speaker on if you want to ask anything. If not, I will see you all on Wednesday. No, yeah, that's right. Monday, Wednesday. Yeah. I'll see you all on Wednesday.